Okay, we are going to another remote talk. This is Minmin Chen from Google Research, off-policy actor critic for recommender systems.
Hi everyone, I'm here to present our work on our policy actor critique for recommender systems. This is a joint work with several colleagues from Google, Chen, Gatto, Devanshu, Jain, Aviral, Kumar, and Achi. So before I dive into the detail of the work, so here are the main messages I hope you can take away from this talk. So first, more sample efficient RL algorithms can indeed lead to improved long-term user experience. Second, while there are a lot of interest recently in terms of introducing pessimism or conservatism into RL in general or for recommendation systems, it's not a one-size-fits-all solution. So what we found is actually for policy-based RL, it actually already contains a lot of pessimism on out-of-distribution actions, and finding the right balance between optimism and pessimism is key to success of RL in RecSys. Reinforcement learning has appeared as an attractive solution for recommendations because it offers a natural mathematical formulations for you to make sequential decisions to optimize long-term user experience on recommendation platforms. So there are three key components needed in building such an agent. There's a state which tries to capture the user's interest and context of a recommendation. So there is the reward, which is used to guide the learning of the agent. So it is critical to design the reward so that it can induce the kind of behaviors you want it to optimize the long-term user experience. And there is lastly, the RL algorithm, which can produce actions or policy which conditions on the user state and try to optimize define the reward. So the algorithm we studied is called the actor critique. So as the name suggested, there are two parts. There is an actor which can output actions conditions on the state. And there is a critique which tries to critique or estimate the value of the action chosen by the actor. So one of the key challenges in applying RL for recommender systems is that most of the recommendation models are actually trained in the so-called off-policy fashion. So it's different from the online settings for traditional RL, where the agents can interact with the environment while updating its policy simultaneously. In our settings, we often have access to a large set of log, which contains historical user item interaction pairs. But unfortunately, these data are often collected by a different and often unknown policy, which we refer to as beta here. So for the actor, we actually follow our previous work. We basically try to parameterize a policy pi theta, which output a distribution over the action space, conditioning on the state. And we learn the policy parameters to maximize the return or the value outputted by the critique. And we apply importance weighting to address the distribution shift caused by off-policy learning. So in this work, we're going to focus on the designs of the critique to actually estimate the value of the state action pair chosen by the actor. What we're doing here is essentially very similar to what we've done for the actor policy. So we again parameterize a critique network which takes the state and action as input and try to output a value of the given pair. So by the MDP definition, the Q value here should satisfy the condition we listed here. So as we can see here, the right-hand side of the equation actually also depends on the Q value of the next state action pair. And we learn the parameters phi of the critique network by basically minimizing the difference between the left and the right-hand side of the equation. So this is commonly referred to as the temporal difference learning. So in our work, we actually try to compare two ways of estimating the target Q hat we listed here. So the approach listed on the right is what's commonly employed in the RL literature. So because we have a function form of the critique network, so it can estimate the value for any state action pair you chose. So as a result, what one can do is that basically is try to sample the next action AT plus 1 prime from the learned policy pi theta, and then you can compute the target as is. So the advantage of this approach compared to what we are going to introduce on the left is there is less variance in learning. Because the next state action pair is often is sampled and it's not seen in the data, so it's out of distribution, which means we have less information on the state action pair, and then the estimation is more prone to error, and the error can propagate through the TG learning. So what we are introducing here is basically want to rely again on the behavior data we've collected. So we take the next state action pair, which is on the user trajectory. And because the action was chosen by a different policy beta, so again, we have to apply off policy correction to address the distribution shift. So the advantage of this approach is that since the next state action pair has already been proposed to the user, so we actually have a lot more information on the pair, including users' immediate feedback on this pair. So as a result, the estimate is more accurate. So the disadvantage is that when the learned policy has deficient support, which means that the learn policy and the target and the behavior policy are very different, then we end up underestimating the value. And then, of course, the importance weighting will introduce variance into learning. So actually, by comparing these two approaches, we find some very interesting observations in our experiments. So the paper actually contains a lot more offline experiments or studies try to tease apart how we designed the critique network, but due to time constraint, I'm going to go straight into live experiments. So we tested the algorithm on an industrial recommendation platform, which serves billions of users. So we run the A/B test for 3 weeks. So the control arm is running a reinforced algorithm with off-policy correction. And then the experiment arm is running the off-policy actual critique algorithm. So as we show on the top left here, so we can see that the off-policy actual critique algorithm actually leads to significant improvement in the overall user enjoyment. And by digging a little bit deeper into what the difference between these two policies, we find that the off-policy actual critique algorithm end up recommending more tail content and more content with shorter length by itself, but leads to a longer-term user enjoyment. And then actually has more serendipitous recommendations that try to introduce users to new interests. So in other words, the off-policy actual critique algorithm actually favors recommendations which has better long-term outcome than those with more short-term reward. So we also conducted a ablation study trying to compare these two approaches of estimating the critique target. So as I mentioned before, one of the key advantages of the approach on the left is that it allows more information to flow into the critique. So, but in this experiment, we actually try to remove this difference. So we actually forces the two critique network to use the same set of features about the state action pair. But even under this control setup, we can see that actually these two approaches to estimate the critique target actually leads to performance difference in the end policy. So the experiment on which is the red one, that estimating the target using by sampling an out of distribution actions actually leads to a worse policy. And then by digging deeper into how the policy is performing online, we actually find it ends up recommending more hard recommendations and content of longer length by itself and more familiar recommendations. So this is exactly opposite to what we've seen before. And it's very surprising to us because we were expecting that by actually sampling out of distribution actions, we will be coming up with a policy that's more optimistic and then instead of myopic. And we hypothesize the reason is that because our actor takes a softmax formulation, so because of the normalization term here, when we are maximizing the expected return, it essentially tries to increase the values of the chosen actions, which has positive returns, while try to reduce the values of any unseen actions. So as a result, the Q value of any state action pair which does not appear in your data, which has not been chosen by previous action, end up having very small Q values. And the critic target is essentially was dominated by the immediate reward. So as a result, the policy end up just being more myopic. So in other words, the softmax policy parameterization actually leads to very pessimistic estimate on any out of distribution actions. And estimating the critique target using behavior data actually leads to a better critique and policy. So in conclusion, well, we are super excited to report that we can still improve the user experience by finding more sample efficient RL algorithms. The key insight we got from the work is that, well, overestimation error or optimism for out of distribution actions is very common in value-based reinforcement learning algorithms. On the contrary, you find policy-based, especially those that employs softmax policy parameterization, actually often end up underestimating the out of distribution actions. And finding the right balance between pessimism and optimism is key to realize the full potential of offline RL for recommendations. Yeah, with that, I'd like to take any questions you have.
All right. Questions are coming in here on the app. A popular question here, if you could talk about what technologies you use to learn off-policy evaluation in large batches. Did you use Spark and how much data was involved in doing that?
Sorry, I didn't get the first part. Which technology do we use for offline evaluation?
Yeah, so what's the setup for doing the doing the learning?
I see. So actually, it's a great question, and I want to point out that offline evaluation is actually very, very challenging for RL in RecSys. And to be honest, I think it's even more challenging than off-policy learning, because for learning you essentially just need to find the right direction to make improvement. But for offline evaluation, you actually have to have an accurate absolute value of the expected returns of a new policy. So we end up actually relies a lot more on live experiments to differentiate the goodness of a policy. But for offline evaluation, what we're doing is we basically take the log that's collected, and then we use close to a billion of user trajectories, and then we train the policy majority of it, and then we reserve about 1% of that trajectories for evaluation. So again, our policy correction is used in the evaluation step to correct for the distribution shift. yeah, to be frank, I think it's still very challenging for to fully rely on offline evaluation to discern the goodness of different policies, just because of the distribution shift.
All right, I think we're gonna have to leave it there. A difficult but interesting problem. Let's thank the speaker again.